Hello.
Hello. Welcome to the stream, boys. Hey,
Oh
everybody,
man,
welcome to the stream.
I forgot to change the insane levels. My bad. My bad.
Oh, bro, we're
Reset.
starting with
Reset.
like the 9, bro. Oh, everything,
Reset.
dude. I was
Reset.
stressed out.
All right, we're here.
We're here. Another stream, another week. Oh,
How you
you
doing?
remodeled your room again.
Yeah. No.
Damn, bro. You going with the summer vibes, with the surfboard, with the beige, with the blues. All
Yeah.
right.
Trying to change things up a bit.
Yeah. I see you.
Tired of the pink and stuff.
Yeah, damn, bro. Hey, that's fast. 1 week to another, and bam, new
Hey,
room.
it's real easy. You just move stuff around.
You just move stuff around,
Yeah.
get some paint easy.
Mhm.
Nah, bro. I like it. Hey, I like it. I like it. Yes, sir.
So what you been up to?
Not much. We went to a hackathon this weekend. You know,
Oh yes, we did.
we it was sour. It was a little bit of
Sour.
sour. Yeah, because we had fun. With the friends, with our group. We watched some UFC fights. We were joking around, and stuff. So it was a great
Mhm.
time. But it was a little bit of bitterness when it came
Some
to the
bitterness.
winners, right? We had a great project. We implemented a couple of AIs, a couple of APIs. It was innovative, never seen before. It
Never
was a
seen before.
PowerPoint assistant that you could like basically create an entire slide with commands through a chatbot. No need of the tools. It was amazing, phenomenal. Applied to elderly, young, anybody, everybody. But then comes a copy paste of PayPal, right? That basically they said, let's all just focus on the front end and make it look nice and make it that I can click on points. We click on, I want to send $20 to this guy, but in reality, you ain't sending nothing. You're sending
Wow.
air.
They're calling you out.
And the only back end, it was the login and the password. Like, what the heck, my guy? What the heck? Over here we were
Tag
different
in.
AIs, different
Tag me in.
APIs, and then tag you in, my guy. Tag you in.
All right. So these judges, I'm sure they're nice judges, right? But like Jose was saying, and I want to preface nothing against the people that won. I'm sure that they worked really hard for that. I just have me personally. I feel like hackathons, in order to win, you need to create something unique. And I feel like the judges might have been looking for something that wasn't unique and something that's already been established before. Because, like Jose was saying, they built a transaction app, but for the university, and it's really nice. It looked really good. Like, I'm not hating. It looked really good. I don't know if it works though. Like, I don't know if they did the back end and whatever. But the front end looked really good from what I saw. But I just think that it wasn't unique. Like, it's nothing new that people haven't
Exactly.
done. Like, there's a bunch of transaction apps out there that could eliminate the use for that product that they made. So I just feel like maybe we're a little cheated out that something unique didn't win, but ultimately we lost. So no excuses
Yeah.
there. I just feel like it wasn't, I wouldn't say fair, but it wasn't what we were expecting.
Exactly.
Someone to win. We were
Yeah.
honestly, if someone was to win, we were expecting them to have like a big hardware component, like a flying
Yeah.
drone and it auto tracks. Like, I would have been okay with that. But a transaction app where there's thousands of them already created, I just don't think that's right.
It's like they
For a
say,
hackathon.
it's like they say, same poop, different toilet.
Wow,
Same poop, different toilet, my guy.
I never heard of that before.
Well, it's, people say, it's the same poop, bro. It's it, but just in different toilet, different restroom, my guy. Us, bro.
Okay.
It wasn't poop, bro. It was amazing. It was beyond. But people, sometimes they go for the looks, right? Not everything that shines is gold.
See, now that's the thing. Like
Yeah.
ours, it was like the chap, like looks wise, it's what we had. Like we didn't have a lot of customized ability because we're going through a certain API extension or whatever it's called, and
Uh-huh.
but what we were honing in on was the vision behind the product, like who it could help, why it
Exactly.
helps, why it's beneficial, blah 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 blah. And I just think it was more unique than something like a transaction app. Imagine explaining why it's helpful. Like we know why it's helpful. It's so easy. You don't have to go to a bank. You can do transactions right off your phone and stuff. Yeah, everyone knows that. It's nothing
But
new.
no, you know, it's
Anyways,
just, I guess,
so
you know.
to kind of change the topic, I lost my voice as well in the hackathon. I don't know if it's because like I'm sick or got any like allergies or whatever it is, but I guess I was yelling a lot. I don't know, Jose, if you care to explain how maybe I lost it.
Well, you know, in the traversy of every project, there's always gonna be haters, right? And Carlos was one of them, bro. I'm sorry, bro. I'm sorry, but you know he was hating it. You know he was for the first 4 hours. We ran into a problem, and then Carlos was like, "Hey, no, we have to pivot. This project's not good. Yada yada." He created another repo for another project. You know, he had all the programming files. You know, Jose's branch, this guy's branch, Carlos' branch. He was ready to go, ready to start typing. He was drawing the whiteboard. And over here, you see us trying to figure out this problem. Like, man, like, come, like, chill, chill. You know, we might have some hope. He's like, nah, bro. You know, sometimes you have to know when to cut the cord. You know, and pivot. And then I don't know why, but as soon as we solved the problem, he became, "Hey, I love the project. I love the vision. We're totally gonna win, bro." And damn, bro, you know. But
Yeah,
at the end of the day, you know, he came back. He came back. You know, but if we did listen to him, I don't know. We probably wouldn't have a project. You
I
know, but
disagree with that, but
I agree with
I
this.
disagree.
I
But
agree with this.
Jose is 75% right. I was I guess you could say hating. Um, but honestly, I just wanted to be realistic with the squad and let them know, hey, we're running into some seemingly big problems that were there was a slim chance of us figuring out because it was one of those unique. It's not coding problem. It's like a system problem why it's not working and stuff like that. And I was like, you know what? Let's just cut it right now and let's do the other project we had an idea
Mm,
on. And
mm.
and they said, hey, go ahead and start creating it then.
We
Don't
didn't say that, but
don't
you know,
lie
you
like that. Don't
know,
lie like
yeah,
that. You said
no,
we'll start it up so that when
no,
we stop it, then we'll just go on it. We don't have to start
not even
fresh.
opening
You said
that.
that, bub.
Me,
Yes.
me.
So,
Those
anyways,
words never came to.
I did that, and then they solved it. Was I upset that they solved it? Yes, because I didn't want to continue the project anymore. I wanted to pivot, but they did it. It took me a while to get back on board, and yeah, we got it done. But anyways, enough with the yapping. I think I'm ready for
Alrighty,
some problems. Are you good?
alrighty. Yeah, we're good, my guy. We're
Okay,
good.
let's switch it real quick. Oh, no.
Yep, yep, yep.
All right, we're here.
We're here. We're
What
here.
do
We're
we
here.
got?
All
What do we
right.
got? Oh, I didn't screen share
Oh,
with you, did I?
no, you did not.
Okay.
I'm just here trying to see when
Big boy.
uh, give me a sec, give me a sec. Okay, I'm here, I'm here.
Okay, so we have uh these three problems. What are the chances we solve three of them in this stream? Not
I'm
very
just
high,
not
but
very high.
we're trying to take it problem by problem.
Yep, yep.
But ideally we want to solve three, and I don't think we can. But I
Yeah,
don't
because
want to
hard
put a ceiling.
ones.
I don't want to put a ceiling on this shit. But
Exactly.
there's a history has shown that we.
Talking talking about ceilings, I remember when we started the project, we were like really into the idea. You were like, "No, guys," and we tried to scope it down because we were going a little bit too far. You were like, "No, guys, don't put a ceiling. Don't put a ceiling. Don't put a ceiling." And as soon as we hit the first problem, you were like, "Nah, let's leave this." And I'm like, "Yeah."
Yeah. Dude,
Anyways.
trust me, man. Trust me, bro. I saw it. I literally saw the vision. I saw that something was gonna go bad, but I was wrong. You know, I'm gonna be real. I thought we weren't gonna complete the project. I was wrong.
Damn, bro. Damn.
Okay.
All right, let's get this. Let's get this. Yeah, we back.
So, we're gonna start with construct binary tree from pre-order and in-order traversal. Honestly, Jose, you should start reading from now on because
Yeah, I got you. Yeah. Your voice. Alrighty.
Not this one. There you go.
This one is just. Let me just note down the number. Let's do 13 minutes. Alrighty. All right. So, while we wait for Carlos, well, we're gonna wait for a little bit for Carlos so he can see the problem first.
I'm here.
All right, he's back. He's back. The man, the myth, the legend is back. So, we got problem 105, and it's a medium, and it says the following: construct binary tree from pre-order and in-order traversal. Given two integers array, pre-order and in-order, where pre-order is the pre-order traversal of the binary tree, and in-order is the in-order traversal of the same tree. Construct and return the binary tree. Huh.
Interesting.
It is a little bit interesting. We're gonna create our own trees now.
So, the binary tree, this is something I get confused about. Binary tree is different than a binary search tree, is that correct?
Yeah, binary search tree, the node or the root has to be bigger than the left and smaller than the right.
And then what's a binary tree?
Binary tree is just a structure.
But like, is there a specific like?
No, I don't think so. It's just a structure where there's a node that has two children. There's a node, there's two children, and stuff like that. But I'm not sure there's a specific structure.
No.
Come on, bro. Lock in, bro.
Hold on. So when we want to return a binary tree, like what I'm saying is, there has to be a specific way to return it because they're giving us pre-order and in-order.
Yeah.
I'm confused about that.
To my understanding, we have to use the function tree node, the class tree node, and the way we just have to define that. Let me see. I think I think that's the way to go.
But I'm confused now.
So we're basically gonna
like we're taking a pre-order version of a tree. Or not of a tree. It's just a pre-order list and a in-order list.
Yeah.
We gotta construct.
Yeah, we have to construct the what's it called?
A binary tree.
Yes.
But you said there's not any particular order of a binary tree.
Yeah.
So can't you just use pre-order and just put it in a tree and call it? So what is the question asking? Like,
it's because like you can go in pre-order and just get every of the children and put them in a tree, but sometimes those children or the broods might have no's, right? Have no children, but you're putting them as a children, right? For example, you can put 3, it's children of 9 and 20, right? And then if you go in order of the array, 15 and 7 will fall on 9.
I see what you're saying.
But this should fall in 20. So we have to use a pre-order and in-order perspectives to see how the tree is structured. And then noticing that how the tree is structured will develop that tree.
So in order is basically how the tree's supposed to be.
Yeah.
I'm not
Yes.
understanding the problem. I don't get
It's because
it.
you
I
have
don't get
you
why
have
we need to use a pre-order.
it's because the
in order.
pre-order.
I know what you said though. I know.
Uh-huh.
If you go pre-order, the list that you get is not accurate because you're gonna say,
Yeah.
oh, 3, wait.
Uh-huh.
This isn't pre-order. This list right here. Is it?
Yeah. It's in
1, 2,
pre-order.
3, boom, boom,
You go to 20.
boom. Oh, ignore that. Nah. Okay, keep explaining. Sorry.
So basically, you're given the 2 perspectives. You're given the pre-order perspective and in-order perspective. We have to mesh these 2 perspectives to see the entirety of the picture, right? For example, and that's the problem. That's where that's the problem to solve. How can we use these 2 perspectives to construct this array, this binary tree? For example, in order, I got 9, right? 9, right? How can I use a pre-order list to know? All right, I'm at 9. How many childrens do I have, right? Or you can use a pre-order. I start at 3. How do I figure out how many elements I have in 9 and 20? Yeah or nay?
How does in order? Can we go to Excalidraw? Can you show me
Yeah.
the traversals again for this one?
Yeah. So in here, right? It's okay.
Ignore that.
Yeah. All good. No worries. So pre-order, we have like this, and we go like that. Post order, in order,
In order.
we go like this. There's 2 ways. So given this, how can we determine the structure of the tree, right? Yeah, but I was gonna say that I was to bring the other one.
And how should the final tree look like?
It should look like this. Because we're not given the tree. We're not given this structure of the tree. We're just given the array representation of pre-order and in order, right? So we depend using those arrays, we have to construct this array, this binary tree.
Yeah.
But how can we use both perspectives or both arrays to build this tree? Like seeing the post in order, what's the pattern to detect? All right, this children has no children. This road has no children. This one does. It's this and this. That stuff. But it's gonna be a little bit complicated. Yeah. Right.
I'm trying to
But
think.
yeah. Huh.
Oh man. First problem.
Starting off strong. I don't think we're gonna be able to do the 3, but let's give it a try. Mm.
Okay. So I guess the main thing is like you mentioned, how are we gonna know if a node has children? That's like one of the things, right? Like
Yeah.
E things. E things. And then how to children, not child, something like that. What's another thing we gotta figure out?
I think that's the main one. I think
Or
so.
what's the main root? Like, what's the?
Yeah, what's the root? Because I think we have to use the pre-order to determine the root. That's for sure. For sure. We have to use. Or wait a minute. No. Yes. No. Huh. Let's see.
I think I have an idea.
Okay.
So, in our recursion call, for example, is there laser? Okay. For example, or in order, we're gonna skip 3, right? In the recursive call, right?
Mm-hmm.
And we're gonna go straight to 9. Is that correct?
Yeah, but I don't think we're gonna use recursion because we already given the pre-order arrays. We already have the arrays, so we're given these arrays right here, which show the pre-order representation, the in-order representation, and based on these values, you have to determine the structure of the binary tree. It's a very interesting problem.
Let me look at the hint, or not the hint, but the topic. It shows. Oh, wrong one. It shows. Oh, okay, hash table, divide and conquer, tree, binary tree array. Okay, so you're right.
Mm-hmm.
There's nothing.
But a hash table. Wait a minute. Maybe a hash table can help us out. We can have a hash table and every element can have 2 children. But how do we determine the children?
Divide and conquer.
This is a very interesting problem. Come on, brother. We got this.
So for the pre-order, can we like already say like this one is a root, this one is the children of? No, you can't say that. You can't. Never mind. Because how do you know in this list? How do you know that 9 doesn't have any children?
Yeah. Or you can do 3 equals 9 and 20.
Wait a minute. Wait a minute, Jose. You know, you know this is the root. You know this is the child of the root. That's a fact. You go into the in order. If the in order is not 9, that means there's another node down here.
Wait a minute. 3.
But that means this wouldn't even be the pre-order. It would be down here. No, it would. But like, look. Oh, let's wait. If you had a node and it was 4, it would be 394, right? This would be. Hold up. Maybe I'm onto something. Maybe it would be. Maybe I'm not onto something.
Maybe.
What did it start from right here and then go? So the list would be 4, 9, 3, 3, 9, 4. If you go to 9, that's the parent. That's the child. And if the child is not the first one on here, then that means. That means first one. If this is not equal to this.
So 9 not equal to 4?
Yeah, because the way like the order is, it's gonna be 4. No, 3, 9, 4, 20. Right? Oh, sorry. 3, 9, 4, 20, 15, 7. This one would be 4, 9, 3, 15. So we know that this is the root, so you can cross that out. We know that 9 is going to be a child of this root. So you check to see if this is the bottom of the list. Like if this has any children left. And the way you check that is if you go to the in order and then you notice that there's a 4 in the front. If there's a 4 in the front, that means there is something more down there. Because it starts off from the bottom. So you know there's a child.
Yeah, makes sense. Yeah.
I'm just throwing stuff. You know, like when you're, I don't know if you ever cook pasta, but you know when you cook pasta and you throw it at the like a wall or something to see if it sticks.
Yeah.
That's what I'm doing. So.
Okay.
Yeah. Hello, Ali.
Okay. Welcome, Ali. Welcome to the stream. But you might be onto something. I see it now. Can I erase some of this just to make it a little bit more clear?
Yes.
Let's see. Because like I said, there's a 3 here.
Yeah.
There's a 3, which represents a node, right? Like a root.
Yes.
If this 9 is not equal to 3, that means it's a child. It's the left child. Then if it's 3, that means that's a root child. right? That is a root, right? So
Yep.
9 root root 3. Now 15 over here. We know since 15 is not equal, since 15 here, so we can say this is not the right child. It's in order.
You're onto something. No, never mind. You're not.
Okay. Thank you. Thank you.
I'm joking.
Wait a minute.
9. And then you check. I think you're onto something. What you just I don't want to like change your train of
No,
thought.
yeah,
but,
switch it up. Yeah, for sure.
But you said right here 3. You check over here. If it's not a 3, then this is the child of 3. And then
Yeah.
to double check, that's what you assume, right? And
I'm assuming that, yeah.
To make sure it is, the next one has to be a 3. Like it has to confirm it. That if this is a 3, that means that just confirms that that is the child. So you do that for 9. You go to 9 and you say, 15 is the child. Let's confirm it. Go to the next one. It's not 9. So that means that's not it.
Okay.
So that maybe means that there's no children in for 9. You go to 20 and then you check then you don't move. You don't move here. And then you check. This is the child of 20. You confirm it. Boom, it is. And then you move over to 15. 15.
You're now at 20.
You're now at 20. And you're like, that's a child. You look to the... I don't know if it works, but then you go to 7. You go to 20. Nah, that wouldn't work.
It works for the left child, but not for the right child.
Yeah, almost.
Because it does make sense.
Music. It's called Instant Gold.
Oh no, bro! It's not instant, bro.
Keep going, though. I'm sorry.
Oh man. Because yes, that makes sense. So for sure, the root and the 9 and 20. What if, right? Call me crazy, I don't know. There you go. What if in here, right? We have 3.
Okay.
Right, we know we go over here, we go, 9, right? 9 is not equal to 3, so maybe 9. Possibly we check 3. 3 is 3, then yes, right?
Yeah.
And then we say, all right, 9 is on my left, I'm 3, and then I have 15. 15 has to equal to this 20. They're not equal, so that's not my 15. So that's not my right child, right? Because my right child is 20. My right child is 20, right? So we say, all right, that's not my right child. Let's move on to 9. 9, that's equal to 9. All right, so 9, it has no children, so we scratch it out. We go to 20. 20 is not equal to 15. So 15 might be right? 15. We can verify by 20. And then we ran into 7, right? Which were right here. We check 7, which is 2 plus. And then, yes, 7 does equal to 2 plus of me. That is my right child. And then yay or nay? I don't know, dude. This thing is a weird problem to figure it out because we don't know how to create an array, binary search tree. I don't know.
I think we're on the right track. I think there's something there. It's just confidence of it. Like, it works. Like, we could try to think of something, like find coincidences to make it work. But will that withstand all test cases? That's what I'm worried about.
Yep.
So what's the definite way to do it? How about let's do what we learned in class. Let's solve the sub-problem of it, which is, let's just get a first tree. Let's just figure out how to get this tree set up from
fair.
You got it?
Yep. Let's break it down.
Break it down, baby. Come on.
3. I'm writing at the bottom, so 3, 9, 20. No, yes, 3, 9, 20. Yeah.
3, 20, 7. You're doing this, right?
Yes, but
But
just for the first 3 numbers.
Oh, yes.
3,
This
9,
one is
9, 3, 20. So we got these.
yes.
So we got 3 and 9. So 3, right? That's our node. For sure. These are node.
In order.
In order, yes.
Keep going.
Just let me give me one
this
second.
is pre-order.
Yeah, pre-order in order. So it's 3, right? Now we go to this array. We say, homie Holmes, what do I need? And then
in order gets the furthest up to the bottom. The farthest left.
Yeah.
So this will always be the furthest left. First num will be furthest left node. Is that correct?
Yeah.
And the first in the pre-order would be the topmost node. We're on to something.
We're on to something.
Okay. I'm here. Okay, so knowing that, keep going.
So we know for sure that this 9.
We know the next one will be a parent of the previous node.
Maybe it depends. Because what if we have more nodes though? More nodes? And let's say we had 10 here.
Oh, sorry. I'm sorry. I'm throwing us off track. All right, we're back on track. Ignore the 10. I'm sorry. Ignore the 10. Keep going.
This 10?
Keep going. Yeah. No. Yeah. Do your thing. I was just trying to
All
jump the
good, all
gun.
good.
Okay.
Let me just select this thing so we can edit the text. Right, there we go. Okay. Let's see, brother.
So you're on the track. You said 3 is the first, is the node, is the topmost node.
Mm-hmm.
So you want to start off with pre-order.
Yeah, I'm assuming so.
Okay.
Let me see at the topics. Hash table, divide and conquer tree, binary tree. Okay. Yeah. Okay. So yes, we start at 3, right? Because that's the node we're gonna give it. Now we just have to determine the children, right?
Yeah.
And the children,
If any.
if any, yeah.
So we know that 9 over here is the furthest left node. But how do we know that this is a child
Of 3.
Of 3? The way we know is if the next thing is equal to 3.
Yep.
Because that means if 9 is the furthest left node, the next thing up will be 3. And that's the next value in the array. So that just confirms to us that that 9 is a child of 3.
We got Dinesh. Sorry if I mispronounced your name. Dinesh, hi dude, I'm a fresher. How to get started with competitive programming like LeetCode, Hacker Rank, Code Chef, like that. To be honest, just start doing it. You know, just start and really understand the fundamentals of like data structures, like data structures like binary search trees, everything related to binary trees, how to traverse them, how to analyze them, how they work, graphs too, dynamic programming and all that stuff. And just start off easy, you know, with the small problems. You know,
you go to our first streams and look at those problems that we were doing, because that's literally how we're in your same position. We didn't know where to start, and those are literally the problems we did to start off. So I know I know we're like just start, but literally just start, and I will choose those problems that we worked on in the beginning. If it worked for us, maybe it'll work for you.
Yeah, and really watch some tutorials on like a data structure, like how they work, how to implement it in a specific language, and then work on that data structure for a bit, and then go to the next one and next one, and I'm pretty sure you're gonna be fine. And slowly but surely. Alrighty. 9320.
Okay.
How do we bro?
Do we want to? So is that do we just want to continue it out? See if it follows through. If it doesn't, then we know it's.
Okay, think about it.
I'm thinking.
What if we put all of these? We know these are the parents, right, of something, right?
Yes. Wait.
What if we put these of you know they're the roots. They're the roots of something, right? A root.
These are the roots.
Because 9 is a root, 20 is a root, 15 is a root, 7 is a root. They're roots. Yeah.
Yes.
Let's put them all in a hashing tree. In a hashing. Pa. Right? And we go to 9. Hey 9, what are your parents? 3. Just put 9 here. Bam. Right now, because 9, now 3 has a children of 9, right? And then we know, okay, 9, cool. Your parents 3. We know for sure that the middle one is the parent right? Because of the next one of a number, it's usually the parent because of a binary search, right? Yeah or nay?
Oh, you're just looking at this and not this though.
Well, because these are the roots. These are the roots.
Yeah,
These are the roots.
but I'm saying like, are we still assuming that we're starting off right here?
Yes, we're starting off at 3.
I thought
Yeah,
you
we're
were just
starting off
checking
at
the
3.
in order and saying 9 is a child. The next one after is the parent.
No,
without looking
yeah,
at
no, no,
this.
no, no, no. But
So
it
you're
is
looking
a
at
fact
this.
that this number, and if there's a number here, this number over here, that's gonna be the parent of this number right here. That's for sure. For sure, for sure, for sure. For sure. Because how does in order work? It goes to the left, parent, right. Left, parent, right. Left, parent, right.
Denise said, "Thanks for the guidance. I'm confused whether to build and work on projects or solve DSA. I say both, but
a little bit of both. You know,
if your certain circumstance prevents you from doing both, then I think always getting those fundamentals of DSA, in my opinion, will be good to start on early. But I could see people thinking projects are maybe more beneficial.
Yeah.
But here's what I would say: projects help you improve your resume. DSA helps you pass the interviews.
Yeah. So it's a little bit of both.
Hand in hand. They both go hand in hand. So it's not whether you choose one or the other. They're both are needed. So that's why I recommend both.
A little bit of both. A little bit of balance here and there.
I would choose to at least get a foundational knowledge first of of the data structures.
Yep. All right. So for sure, we know if we have an element, the next one, I'm pretty sure it must be the parent of that parent, of the left parent. 100%.
So this node will be a parent of this.
Yeah.
Okay, so what if this was... What if... wait. I messed up the order. This is wrong.
Why? No, it's right.
No, it's not. It's supposed to be 15.
No, but we're doing the first 3, no? You said the 3, 9, and 20?
The list, though, is 3, 9, 9, 3, 15.
Oh, you're doing the first 3 of the list. I was doing the first 3 nodes.
Yeah,
like 3, 9, 20.
We're trying to use these lists to build it, but this list aren't even accurate.
Well, that's what we just do 9, 3, 20.
Yeah, but 9 through 20 is not an accurate list, though.
Why not?
Because if it's in order, it's supposed to be 15, the first 3.
Boy, we're just working with a subset of the list, with the nodes.
But it still won't be accurate, though.
Well, we have to use the entire thing then. We have to use
use the first 3.
No, but then we need 22. Because 15, you're saying that there's 3, 9, 15, right? Like the right child of 3 is 15.
I was saying let's focus on building this subtree. But that doesn't necessarily mean just put 3 nodes in the list and try to figure it out. We could use the same list, like the length of the list, and just try to just build this though out of it.
Just a top.
Yes.
So we need a 20 in here.
Yeah, we need it to be accurate.
I think we do need we need all the all the elements then. Yeah. So yeah.
Okay. All right, we're back. No, we're just trying to build the first 3 though. Like we're trying to build the first subtree.
Okay, in that case, fair. In that case, I think it still works. Let me see. Oh, no. Okay, so here, pretty much, I think it works the same. Since 9 and 3 is a parent of 9. Hey, First Shield, welcome to the stream, my guy. Welcome to the stream. No,
First
long time no
Shield.
see.
What's up, First Shield? Hope you're doing good.
So, we go to 9, right?
Okay.
Damn, why is my Mexican bro with his deep voice, bro? What do you mean, deep voice?
Who is he
I'm
talking
talking
about?
regularly. I think he's talking about. Oh, you. He's talking about
The
you.
dog? Oh.
Yeah.
Hey, I lost my voice at a hackathon. I'm sorry. Oh, you know what's
Yes.
funny, bro? You know what's
Uh huh.
funny? One of my co-workers came up to me yesterday, and they're like, I said, "Oh, I lost my voice. Sorry." Like, she was like, "Oh, it's all good, whatever." And then she's like, "Oh, you're partying like crazy, huh?" And I was like, "Actually, the total opposite of partying. It was actually a computer science hackathon and stuff." And it was funny because like she assumed I was partying, because I lost my voice.
Yeah.
And I told her, I said it was the opposite. It was actually a
He's just sitting
nerd,
down.
a nerdy hackathon with my team. What
Yes,
hackathon
sir.
you said, First Shield? It was the UTSA Rowdy Hacks for our university. Yeah. Thank you for asking. All right, I'm back, Jose.
All good. No worries. But yeah, it was Rowdy Hacks. They call it Rowdy Hacks.
Yeah.
So yes, so every node. It was more of a general for Shield. There's no specific like theme. It's just like build whatever you want. It's like you can do cyber anything you want, but there's tracks where they do specialize like AI, cyber, and I think best design. But those are like sub tracks. The main winners and stuff are is just like overall. There's no specific theme or track per se. Yes. So here, for example, okay. Okay, so I know for a fact that every pair of twos, it's a child-parent relationship. Can we agree on that?
Oh.
Every twos is a child and parent relationship.
Wait a minute. Okay.
And every twos on the left and back is a life and parent relationship as well. You see that?
No, can you
Because
get a
if you
different
go
color?
you go from the left to the right, and you can start with twos. Right here, parent relationship. Parent relationship. If you go from here, parent relationship. Parent relationship.
Why did you skip the 15 and then the 7 and 20 you didn't skip?
Because these are not parents. They're not related.
But how do
The
you know
ones
that,
real.
John, by looking at the array?
Well, I looked at the data structure too.
But you can't. We don't know what the data structure looks like.
Well, that is true. Huh.
But I think we're there, bro. We're like digging, like that meme where like you dig and then like that guy's hoping to get diamonds and stuff and he stops and he turns around.
Yeah.
We're there. We're the guy digging.
Oh man.
We're there. We're almost there. So I think you're onto something. You're onto something here. Let me do some erasing real quick. We'll just erase this.
Damn, I'm onto something about you relay. Like,
So we know what this is. There's a connection here, right?
yeah,
There's a connection here, right?
yeah,
And then you're gonna say, where's the connection
yeah.
here?
There's no
But
connection there.
if it's uneven, this goes back to this.
Mm-hmm.
Goes back to this. So we know that 20 has 15 and 7 as its children. Okay? We know 3 has 9 as its child. Okay. Now that we know who's a child of what, now we could say, bet, what's the start node? What's the beginning node? That's not gonna work, man. Just realize it's not gonna work because
I think we should see one of the tips, no?
there's no tips.
There's no tips.
I don't think so.
Is there? You want to go to the discussions and see if there's some tips in there?
Okay. Okay.
Okay, keep trying, guys. Struggled with a similar problem a year ago, but today with a piece of pen and paper, also vaguely remembering the tricks, I solved it in 22 minutes. We've been here an hour. Solving medium is a 15 is standard. Okay, tracks. Pre-order always has a node first, but you don't know the size of either branch. Either in order always has the left branch of the node and right branch of the right of the node, so you know how the size of the branch is. Okay, we know that. We know. So we're in the right path. We confirmed that we're in the right path. We're in the right path. We're in the right path.
Wait. How does it? It says it's a tip. Like, how do I search for more?
Tips.
Yeah. Oh, okay. Oh, just motivation.
Plus recursion. Damn.
I think that's the way to do it, but oh man. Oh. 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 I got a cramp.
All right, let's see. We got an hour left to study this, comprehend the problem.
Oh.
And it kind of just worked. Try constructing a binary search tree where the items in pre-order are inserted and compared based on their indices in order. And the root is pre-order 0. Yes.
Yeah.
Hmm. All right, let's go back to the drawing board.
Okay.
Wait. What did you say there?
It just said they didn't know that pre-order and in-order consist of unique values. They're not saying both of them are all
Okay.
going to have unique values, but that those lists themselves, there's not going to be no repetitive values.
Yeah. Makes sense.
Okay. Want to go back?
Yep.
Okay. Where are we at?
Oh, give me 1 second. All right, there you go. I'm good. Oh, okay. So pre-order, we got index 0.
Yep.
Bro, this thing is garbage, bro.
Okay. Hold on. Break it down. So 3. Boom. Then.
Bro, come on, bro. I wanted to draw it, bro. I wanted to draw my hash map.
Bro. It doesn't look good.
Doesn't look good, bro. That's how we're gonna be winning the hackathon, making it look good. Bro, I'm still mad at that, bro.
3. We got a root. We know this is a root.
Mm-hmm.
We know because it's the first of the pre-order. Keep going.
Okay, so we know it's a root. How do we determine the left and right children? The left and right children, we know for a fact. Huh. See, let's play around with it. Divide and conquer. We got 9. Okay, listen to me.
Okay.
Listen to me. We know 3 is the node, right?
Yeah.
Right. Why do we go to 3? And we say, give me the left one and give me the +2. If there's no +2, that means if +2, right, give me the +2, which is 20, right? Now we got 3, 9, and 20, right?
But okay.
But this
Go.
wouldn't work
Keep
for
going.
9, though. This wouldn't work for 9. This wouldn't work for 9. This wouldn't work for 9.
Okay. How about this? 3. We could immediately put that in the hash table.
Wait, where's the laser?
All the way on the right.
Oh.
Yeah, it's kind of hard to find. Yo, why is yours? Whoa. Why is yours pink?
Why is yours pink? I see yours is yellow.
Mine's red.
Mine is red. I see yours is green. Yo. Discrimination up here.
Okay.
So we got 3 in here.
Okay, now let's move. Let's move to the next one.
Burp. Yeah.
9. Now that you moved over, right?
Uh-huh.
In the pre-order sense, this would be it's a medium problem first shield. It's this one right here.
Yeah, it's 105. 105.
If we move over, we could assume that this is at a lower depth than the first, right?
Yes.
This, this
Someone.
any node after. I'm gonna put that here. Any node after is a child. Can you assume? Can you agree with that?
Child of what?
Any node after in the pre-order is a child of 3. Like any the next node after 3 is a child of 3.
Yes, these two notes right here. Yeah. Yep.
No, but I'm saying 9.
Yes.
Okay.
Yes.
So we could say for sure 9. We know the next one will always be a child of 3. This will differ.
The next two.
No, not the next 2. Because if there's a 4 right here, then it's
Oh.
going to be a 4.
Yeah. Yep.
So, but we know that the next one would be. So, we could say that definitely.
Okay, so we can say that 3
that,
and 9 have a relationship,
yes.
right?
In the in order side, we could say for sure. No, we can't say for sure. But wait, can we say for sure?
Damn, this problem is giving me some.
Okay. Now we're gonna move over. We're gonna move to this one, 20. 20. How do we find out whether 20 is a child of 3 or not?
Well, that's the thing. We can. What we're given, or it's super easy to find the left child, but not the right child.
Here. To find out if 20 is a child of 3.
Is that a hard problem? It's a medium. Yes. I think you answered that already.
I did, yeah. It's all good.
Okay.
After, to find out if 20 is a child of 3.
What if we start from the reverse?
No, Jose, I think we're there. I think we're here. Come on. Right here. How do we find out if 20 is a child of 3? If we have 20, or maybe we start over. Maybe we say, okay, we got the first 2 figured out. Let's go to 20. Let's go to 20.
Let's see. So we got 3.
So we skip. Since we got the first 2 figured out, we got 9 and 3 already sorted out. Then we're left at 15. And this is where the algorithm starts. And that is we know we know.
Yo, Orcas, welcome to the stream, Orcas. How you doing, my guy?
How you doing? Okay. Oh man, we know that if we're going by 2s, that, like you said earlier, this is a relationship.
Mm-hmm.
We know that.
Mm-hmm.
And if that's a relationship and 15 comes after, which is the same number right here, then that affirms that 15 is a child of 20.
Mm-hmm. Yeah.
Doing all right. We just came back. We just got done with a hackathon over the weekend. I lost my voice, and that's about it. That's where we're at.
And now we're suffering with this thing.
Okay.
My
Revert it
head
back.
doesn't hurt. My head doesn't hurt because I'm still trying to understand.
I'm almost there. Hold on. I'm almost there.
I'm still
Oh,
trying to
shit.
understand like what's going on with this problem.
Okay, ready again. So we're gonna shift it. So the first two, right? I'm gonna select this. I'm gonna group, and then you're gonna shift over each time. So you're gonna say, oh yeah, these belong with each other. You're gonna do this. And why do they belong to each other, you say? Well, you're gonna confirm it over here. You're gonna say, okay, boom. That confirms it right there. Then you're gonna go to 9 and 20. You're gonna be like, all right, 9 and 20. If it's pre-order, then this technically 20 should be a child of 9, right? That's what you'd be thinking. But if you shift over here, in the in order, we know that in order it's gonna start from down, go up, go all the way down. It's gonna go all the way down. It's gonna go all the way up. Then it's gonna go down, go up, go down. So if darn it, man. Oh, okay. If this hits a root that we already assigned, right? That has a child, that means this went up. This is up. And that means 20 is not going to be below 9 because we went up. So 20 is not going to be down there. So this, you shift it over. You shift over. Now we're here. Then we got 20 and 15. And then you say, okay, if this is pre-order, it should be going down. So 15 should be a child of 20. To confirm that, this
Which is over here. Yeah.
You confirm that with this. You move it again. So now you calculate. Now you say, okay, 20 and then 15. And then you shift over again. Shift over. And then, 15 and 7.
I mean,
15
like you said, here, we haven't touched that node beforehand, right? That means that we went down. We're going up or down?
Well, I guess what I could say here is that this pre-order, we're assuming that 7 is going to be a child of 15.
Wait a minute. Guess what? We can check butt. 15 and 20. Okay. I wasn't expecting that one.
I never know when you're going to throw one at me.
Oh my god. Damn, bro. You're wild. Fair enough. But guess what? Guess what?
What? Chicken butt.
Oh, bro. You got me, bro. So, like you said, right? We take 2015, right? That means that's the left child. But this one includes 15 and 7, right? And according to our beloved in order, it's going to be the root and then it's children, right? Well, here, guess what? We have the children in here. We got 7 in here. We just have to check if this 7 is inside of this substring. And if it is, it's 7. Your name.
Okay.
Like, all right, let's run it again. You go, you do it, because you're the mastermind behind this. So I'm gonna let you explain it over
honestly,
again.
I didn't know how to explain the last one, so let's go back though.
Yeah, so 3 and 9.
Okay.
I'll be in charge of the of over here of the hash table. I'll be over here.
I'm gonna write this just so I can remember. We assume the next the second element is the child of the first. Okay, that's what we're assuming each thing. And we're using the in order to prove us if we're right or wrong. We assume that the second element is above, is a parent of the first element. Something like that. Okay. So anyways.
Yeah. So we have a hash table.
3 and 9. We assume 9 is a child of 3.
Okay.
To confirm
9,
that, we say, is the second element 3, which should be a parent of the first element, which is 9? It is. So that means let's move it over. That's a child. That means 9 is a child of 3. We move it over.
You skip 9. There you go. There.
We assume that the second element is a child of 9. So is 20 a child of 9? Let's go check over here. Well, we're at 3 and 15. These are totally different numbers. And since we know we already have 3 in our hash table, that and we know that I think what I said last time was that since 3 is a value, is a parent of 9, that 3 should be above. Like 3 is above. It's higher. Oh man, I lost it. So what I'm saying is, if we went up in this order, I lost it, man.
I mean, if 15 is in there, you're going down. You're going 2 levels down, 9. Now, so you can say that you can say, because 3, 9, and 20, right, are the children of 3. Right? So we already verified that 9.
How do you know 20 is a child of 3 though? You don't know right now.
Well, that's the thing. That in order, the way in order works is that you go for left and then right child. Yeah, and that's what I'm saying, like, to go from the bottom to the back.
No, so you're saying that if this doesn't have 20 in it, that means that confirms that 20 is a child of 3?
I think so, yeah, because what I'm trying to for this problem might work, right? But I don't know if about other ones. But since the children, since it's left root children, root left and right, we can say from the beginning, we can say, all right, is 9. 3 is a common factor, so we put 3 in there. Now we have 9. Is 9 in this substring? Yes. So 9 is children, the left children in this case. Then we go to 9 and 20, go 9, 3, and 15. We have a common 15, 3. But we know for sure that we're going to determine where the children are. What's the children that we have? By the pre-order. So 15 is not included in 20. So that means that 15 is not a children. All right. So we don't add it to the 3. So we go to 2015. Right. And we put 9 in our hash table. If we go to 20, put it here, we have 15, right, as our children. Over here, we move this one over here to 20. 15 is included, common factor 20. 15 then. We moved both right here. 20 is a factor, 7 is in there, 7 is in here, and then we put here 7. 7, and then we put here 15 and 7, because they're also nodes.
Okay, so if I'm getting you correctly, right here, if there's no common number, that means 9 has no children.
No, I'm saying that if there's no common denominator, yeah, pretty much, yes. Yeah, you said it correctly. If there's no common in between, 9 has no children. Because for a fact, right, if 9 had children, 9 would be placed here, right? 9 would be placed here, and 9 would be here, and it's following children. And over here, like we said, it's root left, right. So children left will be here, children right will be here. And for this one, 9 over here, it would be children left and children right. If 9 had children, right? So now, if we do the box method, we go L like this, we go like this, which is the common denominator, which is 9, right? It'd be the left. And then over here, right, we'll grab these two. Boom, common denominator right. And that's how we know, all right, they both belong to the left because they're both children to the left, to 9. Because if 9 had children in pre-order, they will be right next to it, right next to the right next to 9. And if it had in order, it will be left on the left and right on the right.
Okay.
But I don't think it would work when there's multiple children. For example, let's take this picture. Let's put it down here.
Bro.
Sorry.
No, I was gonna change the topic.
All good.
It's white.
It's white?
Yeah, I got you.
Oh, I'm getting the same problem I get with you. Yeah. Because when my screen is black, your ink is black too.
Oh, okay.
Yeah, something like that. It's weird. But all good. So imagine 3, 9, 20, 3, 15, 7. Pre-order would be 3, 9, 3. No, let's make this number a little bit better. I don't like this number. Let's make it 10. Right? We go to 10, then we go to 20, then we go to 15, then we go to 7. In order, that's pre. In,
3,
we go 10, 9, 3,
3,
15,
15,
20,
20, 7.
7. Yeah. So that's our pre-order. So here we check like 3, 9. You see, our method wouldn't work here because now 3, the children of 3, which is 9 and 20, are further apart from each other.
Well,
So,
let's test it out.
okay,
So
let's see.
let me just do that.
So let's say,
Get this. Bring it over here. Boom. Boom. You really like doodling on here, don't you?
that's because I don't want to open a text box and be like, when I have a mouse and when I can, like,
Okay.
And my handwriting is not that bad either way.
What is this over here? That's a new number I've never seen.
Oh my God,
What
brother.
is that, like a peace sign?
There, that's a 5.
Then what is this? I see this in like
That's
those cavemen.
that's a 0.
No.
No.
Control Z.
No,
Control
I'm not
Z. I
gonna
want you
control
to
see
see
that.
it. I want you to see it before.
That's a
Bro.
0.
That is like some things you see in the cave walls. Those symbols you see in the Egyptian walls, man.
Damn, bro, we have to be specific in here, bro.
Okay, I'm sorry.
I'm gonna type it out in all letters, all different languages, just to make sure.
Okay. So, all right, where are we at? 3 and 9.
Uh huh. You know for sure that 3 is parent.
Root.
Yeah, and 9 is a root. Uh huh.
Okay. So we know that we can move over.
Well, you didn't verify over here though.
But we know that we don't need to verify because this is always true.
True. Okay. Yeah.
9 and 10. We assume the second element is a child of the first.
Mm-hmm.
And to prove it, we have 9 and 3, in which we assume that the parent is that the second element is a parent of the previous, which we can confirm by this right here.
Yeah.
So that means this holds true, that 10 is a child of 9.
Wait, how?
Because over here we confirm that 3 is a parent of 9.
Mm-hmm. But you
here,
left out 10 though.
Over here we're assuming 9 is a parent of 10.
So you're assuming, let's say 3. So these are the nodes, right?
Look.
And every element is a node.
For pre-order, we assume the second element is a child of the first.
Mm-hmm.
For in order, we assume that that second element is a parent of the first element.
Yeah.
Okay, so with that being said.
But over here, you skipped 10 already though.
Where?
Right here, right there, you forget about 10.
But I'm saying that we have 10 right here. So
we just put 9.
9, yeah.
10 and another 10 over here because it's another node.
Is that since we assume the second element is a parent of 9 and this is in order, that this is only gonna be down of 9. Like this is gonna be below 9, which makes it a child of it. That's kind of my explanation. Next one, 10 and 20. 3 and 15. If there's no common, hold on. If there's no common number, then we know that there's no children for there's that 20 is not a child of 10. There's no common. There's nothing. So we move. 20 and 15, back to the same thing. That rhymed. Kind of. We know that 15 is a child of 20, or we're assuming. We confirm that right here by saying 20 is a parent of the first element. So that's true. Then we move over again. We say that the second element is a child of the first, but we see whether that makes sense over here. And does it make sense? Does it make sense that 7 is a parent of the first? No, it doesn't. Because I don't know why, but what we could justify, but that should be, we should say that 7 is a child of 20. Something like that. Something like that.
Get you. I understand.
But I will
You
agree
missed.
with you.
You missed a important point. 3 has 2 children.
Well, that's the thing, is that we know that these are connected to each other, right? We know that 3 and 9, and then 9 and 10, and then 10 has nothing. So where else does this go? Right there with 3. That's just the other half. This. If there's no
We're just gonna so we're just gonna assume?
No, that is true. If there's no linkage based on this algorithm that we have, that's the right side of 3.
I don't know. There's a better way to do it.
This is the way. You know the way? This is the way. But I'm not saying this is final, because I understand that there's definitely some quirks right here when it comes to like whether you just skip the first, move over to the next one, and then how do you know that like you gotta like 3 is above, like it's kind of, I'm just trying to see it in like a human form, like a pattern. Like we're trying to solve it like human wise first. Like how do we see the pattern? So whenever we find out the pattern, then we can know how to code it in computer language. But we're having trouble finding the pattern or algorithm. What are you thinking?
I'm trying to see. Not sure. I'm not sure. Still thinking about it. Because I don't know if you remember the 2i times 2 plus 1 in the 2i formulas.
I tried to call me out like
that.
Why'd you have to call me out like that?
No, I'm just saying. Like, if you remember.
Yeah, I remember. Yeah.
Do you?
Of course. All right, look. You see what you're doing there?
No, yeah. You started. I wasn't calling you out, but you said I was, so now I am.
You don't believe me.
I believe you.
I need some inspiration.
They're the indices. Like you can measure the indices. For
Okay.
example, if this is 0, I think it's plus 2. Mistaken. 0 times 0, 2, 0. So this be index 1. 0 plus 2, this is index 2. Wait. No.
This music's going crazy.
Yeah?
Oh yeah.
I'm gonna look it up, these formulas.
Bro's bringing up the equations. Oh,
The
no, we're cooked.
equation. The equations. But I
We're
think
cooked.
to yeah. Yeah, it's like this, I think. Oh, okay, never mind. This won't work. This won't work. This won't work. This won't work. Because it's for these equations are for these are for complete binary trees. Not quite for baby lover, Julia star, hey lover, I love you just the way you are. Okay, never mind. Let's get back to track. Let's focus up.
What song was that?
Lover.
Dude, guess what I made yesterday? Side note, I think we need a mental break, man.
Mental break. Yeah,
Real
yeah.
quick yap session.
Uh-huh.
Yesterday, guess what I made
Miguitas.
for dinner?
Miguitas.
No.
No?
No.
Okay. Tamales.
No. I made them. I'm gonna give you a hint.
Uh-huh.
It's fish. There's fish in it.
Oh, sushi bros.
I wish I made that, but no, I don't know how to make that. I made salmon and mashed potatoes.
Okay.
Why do you make that face?
Salmon and mashed potatoes. I mean, never tried the salmon before.
You never, but you don't like
Never.
fish, don't you?
Never fully tried it. I tried a couple times, and the couple times I've tried them, it's all right.
All right, well, let me put you on. You get salmon.
Uh-huh.
You put some steakhouse seasoning. Right?
Okay.
Then you put in the air fryer. 10 minutes, 14 minutes. That's all you need. Put in the air fryer.
Okay.
Cook it. Take it out. Remove the skin at the bottom. There's like the scales and stuff. Remove it. Put it in your bowl of mashed potatoes. And not a lot of mashed potatoes. It's like a fist size of mashed potatoes.
Okay.
And you mix it in. You mix it. I forgot the broccoli, so I didn't have any broccoli. But ideally you have broccoli as well. You mix it in, bro. That's like, you could literally make that and eat it all the time. It's so good.
Really? Okay, yeah. I'll try it out. Next time I get some salmon or go to the HEB, I'll try to get some salmon.
And you gotta make your own mashed potatoes. Real easy, man. You get one.
I just get the ones from the HEB, bro. Open the pack, powder ones.
No.
Stir for like 2 minutes.
No.
Easy, bro.
That's like astronaut living. Like you're living like a military person. Why do you
astronauts are living pretty nice, dude. That thing is really good.
Your mashed potatoes and mixing it and heating it up. That's
because it's easy, it's straight to the point, the creamy, it's nice, it's everything fast, quick.
You're not in the military.
No mess.
There's no need.
No mess.
Like so you
anything.
You get a mashed potato. You get a potato. You peel it. You put it in boiling water, right? You do the test, the fork, and you see if it's easy to put the fork in. Then you drain the water. You put the potato in a bowl or whatever, and you mash it. You mash it.
Uh
Right?
huh.
You put salt and pepper, butter, and buttermilk.
Buttermilk.
Yeah. Well, I think you
What's
could do some other type of cream or whatever, but like any milk or anything like that, just to give it some cream to it.
or you could go buy the powder ones. You
No,
go
no, no.
with water, stir
I
it for a
just
little
gave you
bit. Ta-da!
I gave you three simple or four simple ingredients for this. If you go in those mashed potatoes and you look at the ingredients of it, I could 100% confidently say you couldn't pronounce some of the ingredients that are in there.
I mean, it's good, brother. It's
Oh, I'm not saying
good,
it's not
bro.
good. I know it's good. I know it's really good. But I'm
Not good
just
for the
saying, bro.
health.
No, I'm not even saying that either. I'm not like trying to be this health guy. But I'm just
Nah, I'm
saying,
good.
like,
I'm good.
bro, four simple ingredients, man, and you made something really good. Like, I think anyone will be like proud. Like, wow, like it's only
You're
four
right.
ingredients.
You're right. You're right. You're right.
But
I'm
I'm,
gonna try
yeah,
next time. I'm gonna try next time. I'm gonna try next
like
time
it
because I
makes it
do eat.
easy. If you want to recreate those bag of astronaut food of mashed potatoes, you can. But good luck because there's a lot of different things that are not
How
readily
many
available
potatoes
to us.
do you use? How many
I just
potatoes
use
do you use?
one.
All right. Okay. Okay.
But I
Okay.
use the
I'll
golden
probably use
potato.
two.
The gold.
Got it in your stream software. You have to restart it from your end.
No way. Okay.
Okay, it went out. It left. Now I think we're
Oh, we're
good now.
back. Okay.
We're back.
We're
We're
back.
back.
We're back. All right, I'm back. All right. Sorry. Maybe that's a sign. I need to stop yapping. Okay.
Start
Let's go.
yapping. Alrighty. Okay.
So we want to erase this then.
Yeah, bro, my head is starting to hurt now.
Can we get some inspiration? Maybe we could like search it up.
I'm down. I'm down because we spent a couple of minutes here trying to understand this thing.
Ah, well, we actually spent the whole stream.
That is true. So I don't know if you want to get some tips.
Yeah, let's how about you go into the GPT, you give it the question and you just say don't give us the answer, but give us like some hints or some tips.
Okay.
And
Okay.
then screenshot it, send it to me, I'll put it right here on the Skeleton.
Okay. 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 Okay.
But we just need some tips, man. We just need some hints. I'm really digging the music, not gonna lie.
Yeah, I have my
Yeah.
own Spotify in the background,
Oh,
and I found out this artist that she makes really cool like calming music. Pretty
okay.
nice. So I'm just playing it in the background. Okay. But what are you listening to right now?
Instruments.
Okay. All right. All right. I'm gonna put it here in the Scotty draw. All right. Put it at the bottom of the Scotty draw. DNA.
Hold up. Okay. Explain.
Yeah. On the bottom.
I'm here.
Here. You're here. Okay. Okay.
Yeah.
Okay. It says understand the pre-order in order to traverse this you. Oh man. It lists nodes in order, root, left, subtree. Just as yes, we understand. Identify the order in pre-order. The root in pre-order. The first element in pre-order is always the root of the current subtree. Locate the root in an order. Find this root in order list to determine which elements belong to the left and right subtrees. Elements on the left of the root in order belong to the left subtree. Elements to the right belong to the right subtree. Divide and conquer. Use recursive calls to construct the left and right subtrees based on the divided sections of the pre-order and in order arrays. Think about the base case. When there's no elements left to process, return none. Right? Optimize with hashing. Use a hash map to store the indices of elements in order array. Right? For faster lookup times, which helps avoid repetitive scans. Yeah or nay?
Did you understand that?
I understand the divide and conquer a little bit. Look at the root in order. Which one is in order? This is in order. Okay, so we get the or root in pre-order. Okay. But divided sections. What do you mean divided sections?
Wait. Oh, Jose. Oh,
Oh.
Jose.
Yeah.
We know the root is 3, right?
Uh-huh.
It said in the in order, find the root. Everything on the left side is the left part. Everything on the right side is the right part.
That's what I'm saying. But
But
because that makes sense, right? But 15 is not the child of 3 though. It's 20.
I know, but that kind of just tells us that that they're dividing and conquering. Remember. So if we oh, I'm onto something. So 3 is the root, right?
Uh-huh.
And then you go 3. Okay, left side of 3, that's on the left side. Right side of 3, boom. 9. For some reason, we're gonna have to figure out a way that 9 over here, there's nothing on the left.
Wait a minute. You're onto something.
20.
Wait.
You go to 20. 20 has 7 and 15. And then 15, you already used these. So
Hold on a minute. You're onto something, my boy. You're onto something.
I'm here, baby.
You're here, baby. We are here. You're onto something.
Right.
So we do recursive cause based on the pre-order, right? For example, we go to 3, right? We go recursive. Oh, okay. Let's go recursive. Oh, I don't like how thin this is. We go to recursive, right?
You just type it out.
Recursive. Oh no, brother. No. Recursive right here, right? We input node, the current node we're in. Right. For example, 3. Right. Oh, All right, let's assume it works, right? No, we put a node, we have a node, right? Based on this node or indice. Oh my god, I'll write it out because this guy's I feel like you're twisting in your
I didn't say anything.
But I could feel it. I could feel the stare down. All right, so we got recursive, we got node, and the in order pre-order, right?
Okay.
All right, this is too big. Oh my god, I can't. Oh, I can't get it drop, bro. Sometimes it's being super. Give me a sec. There you go. Right here. Boom. Right? So we get a recursive pre-order. And we do let's see. If node or index in this case. Right? Because my idea is right that we have this array, right? 9, 3, 20 and stuff. Yes.
Okay.
Yeah. We're getting a 3, right? We go to that 3 and then we send all of this in a recursive call, all of this in a recursive call. Right?
Okay.
Yeah.
Okay.
Right. So we return that in a recursive call. So node or index in this case. If index is less than 0 or index greater, pre-order the length of it. The length of that, right? That means we went up past the out of bounds. We have no more elements to work with. So guess what? We return none. Else, if not, they call index plus 1 pre-order, right? Right. But now, no, we're sending the array. We're sending array.
Hmm.
I'm confused, brother. I don't know. I think we had it.
Let's see. Let's try it again. 3 is the root. You go to 3. Everything on the left is going to be on the left side of 3.
Yeah.
On the right, it's going to be on the right side of 3. You go to 9. Everything on the left side of 9 going to be there. If the next node on the next side of 9 has already been searched, that means there's nothing. Then you go to 20.
Yeah.
You go to 20, everything on the left. Remember, you stop because this one has already been searched. So it's going to be this one and this one. You go to 15. Again, you already searched 20. You searched 3. So it's just going to be 15 is left by itself. 7, same thing. Nothing on the right, nothing on the left. And that's it. That's it. 3. Go to 3.
So it'd be the recursive call would be the divide and conquer would be 3. Then we got an array of 9, and then we got a 15, 27, right? And then 9 would stay there. Then 20, this would break into 15 and 7. Right? Yes. 15 would break into, would return nothing. 7 would return nothing. Would return none. And 20, this is the right child, right? Without PTR, we equal to this, which now, so we're not going to return nothing. We're going to return 15 over here. Oh, I'm on to something, my boy. I'm on to something. You see me? Yeah, or nay.
Where are you at?
Right here. Okay. So 15 is going to come over here. 7 is going to come over here, right? Because it got split. And then we're going to return 15. We're going to return 7. Now, this is a left, this is a right. And then we're going to return 20. And over here, we're going to return 9. This is a left, this is a right. We got the logic down.
Brilliant.
Yeah. Okay. But now how do we translate it to the array? How do we break it down? Because it's 9 and 3, 15, 27. That's a different row. So we have to go based on the in order to determine which ones are the roots. which ones are the roots, right? So we're gonna say index of 3, right?
Mm-hmm.
Oh, that's why we need a hashing, right? Because we're gonna have a hashing where it's gonna be 3, 9, 20, blah 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 blah, all with their index, right? Yeah. Yeah. And then we're gonna say, all right, homie. Wait a minute, no. I don't know, brother. I don't know.
It's already about to be 12.
You wanna call it here and leave it
I
on to the
think
next time?
I think so.
Alrighty. Yeah, because I know we you got things to do. So yeah, I think we can call it here, buddy. We're not gonna erase anything.
No.
We're gonna leave it here until next time.
Yeah. All right, Jose.
All right, buddy. It was a little interesting stream per se, to say the least.
Yeah, I mean it was challenging. I like the problem, to be real.
It's
We're getting
interesting. It's
somewhere,
interesting. I like it. Yeah.
but it's just not the outcome we wanted.
Exactly.
But I think that's it. I think that's all for me.
Same here.
I wish we saw something.
Yeah, but hey, sometimes we have our ups and sometimes we have our downs. Like last stream, I think we finished 3 problems, so we'll go up and down, up and down, up and down. But hey, at least we understood the problem. We have a slight solution that might work.
Yeah.
Yeah.
All right.
All right, my guy.
That's it
I'm
for
gonna let
me.
you go. Yes, sir. So, guys, hopefully you guys enjoyed the stream. Make sure to subscribe, like, and share. So we apologize for not solving this problem, but it's a pretty tough one trying to just wrap our head around it. And hopefully next stream we're gonna be able to finish it. So I got nothing to say, and I think Carlos does also have nothing to say. So I wish you guys the best morning, afternoon, evening, night, whatever it is. Just have a great day. And we'll see you guys next time.
All right.
All right. Bye bye.